To peer across the cosmic dawn and directly image Earth-like exoplanets, modern astrophysicists require massive, extremely sensitive observatories. But those ambitions are restricted by a strict physical bottleneck, the volumetric dimensions of the rockets carrying them to orbit. Even massive next-generation architectures like SpaceX's Starship dictate a rigid, inescapable maximum payload volume. You cannot fit a 6.5-meter primary mirror inside a 5-meter cylinder. To overcome this diameter limit, the aerospace industry had to abandon monolithic structures entirely. The telescopes had to be folded. Folding a spacecraft, however, introduces massive risk. On April 11, 1991, the Galileo probe was en route to study Jupiter and its moons when it initiated a critical maneuver. It attempted to deploy its 4.8-meter high-gain antenna. The mechanism relied on a traditional umbrella-like design, using rigid ribs, rotating pins, and ball screws to push the structure outward. It locked up mid-deployment. After enduring multiple gravity assists past Venus, extreme thermal cycling had degraded the antenna's solid molybdenum disulfide lubricant. Exposed to the freezing vacuum of space, unlubricated metallic hinges experienced severe galling. Contact stress caused localized plastic deformation, essentially welding the joints together. When a deployable structure relies on hundreds of traditional sliding and rotating joints, it creates hundreds of single points of failure. Every gear, pin, and hinge becomes a liability waiting to freeze or bind. To build larger observatories, engineering mechanics required a completely frictionless approach. They needed a mechanism where a single continuous topological sheet could deploy itself without interlocking parts. The solution originated in the mid-20th century with Akira Yoshizawa. By inventing wet folding, dampening paper to allow for organic curves that dry into rigid structures, Yoshizawa elevated origami from an aesthetic craft into a precise geometric system. His standardized folding notation inadvertently invited physicists to analyze the intrinsic physics of the crease, treating a continuous flat sheet as a strict two-dimensional manifold. This led to the definition of rigid foldability. A flat plane can be broken down into specific vectors, such as degree 4 vertices, where exactly 4 crease lines intersect at a single interior point. This specific geometry turns the entire sheet into an over-constrained mechanism with a single degree of freedom. Actuating a single dihedral angle at one edge deterministically forces every other crease in the network to fold or unfold in unison. A massive, densely packed space array can therefore be deployed in a highly predictable, mathematically flawless sequence through the pull of a single motor, bypassing the friction traps that doomed Galileo. But to shape an optical sunshield or a parabolic dish out of a flat surface, engineers have to navigate a strict law of differential geometry, Carl Friedrich Gauss's theorem agredium. Gauss proved that it is physically impossible to bend a surface with zero Gaussian curvature, like a flat sheet, into a surface with positive or negative curvature without stretching, wrinkling, or tearing the material. Origami provides a geometric loophole. By confining all spatial bendings strictly to the straight crease lines, the flat facets between them maintain zero curvature locally, even as the overall macrostructure forms a curved shape. The ultimate aerospace application of this rigid foldability is the Miura-Ori fold, invented by Japanese astrophysicist Koryo Miura. This diagram compares material behaviors under tension. On the left, a standard material exhibits a positive Poisson's ratio. When longitudinal tension is applied, it structurally narrows and thins out at its center. On the right, the zigzag geometry transforms the Miura fold into an auxetic metamaterial with a negative Poisson's ratio. Pulling it in one direction causes it to structurally expand outward along all axes simultaneously. Yet, theoretical kinematic equations assume a material thickness of exactly 0. If you apply a Miura pattern to solid carbon fiber or thick beryllium, the facets will physically intersect and crush each other upon folding. To transition these mathematical models into orbital hardware, researchers rely on thick panel origami. By utilizing offset hinges and axis shifts, they physically decouple the mathematical rotation axis from the rigid material's edge, granting the panels the spatial clearance needed to swing cleanly. Bypassing these physical limits requires mapping this exact auxetic geometry onto highly stiff, directional materials, allowing engineers to precisely tune the stiffness and energy absorption of the deployment sequence. The most complex manifestation of these principles to date is the James Webb Space Telescope, constructed with golden hexagonal beryllium mirror segments. To detect the faintest infrared signatures from the early universe, its optical instruments must be heavily shielded and passively cooled to a continuous operating temperature of roughly 40 Kelvin. That extreme thermal isolation relies on a tennis court-sized sunshield made of 5 distinct layers of aluminum-coated kapton. The sun-facing layer is just 50 microns thick, and the subsequent layers are a mere 25 microns thick. Packaging and unfolding this massive, fragile membrane carried immense risk. The mission cataloged 344 single points of failure, with 80% of them tied directly to the unspooling sequence. Unfolding the shield on Earth induces localized friction and sagging that simply does not exist in the microgravity of a Lagrange point. Successfully executing the dynamic release of these layers in space relied entirely on advanced strain energy mapping developed through computational origami. Spacecraft are no longer static, rigid objects dependent on vulnerable mechanical joints. Through strict geometric discipline, the ancient craft of paper folding has become the definitive, frictionless blueprint for expanding our reach into the vacuum of space.